the beginning, there was no grand city of stars and no sweeping bridges of galaxies. There was only a newborn cosmos filled with hot light and particles racing in every direction. It was a place where nothing yet had a reason to stay close to anything else. Then gravity arrived as the silent sculptor. It did not shout. It did not command. It simply tugged. Every tiny grain of matter pulled on every other grain. At first, the pull was small yet patient strength, the kind of power that needs time, and the universe had plenty of that. What looked almost perfectly smooth in the earliest moments held minuscule differences in density. In one location, the soup of particles was ever so slightly thicker. In another, lighter. Those invisible wrinkles were enough. Gravity noticed them and began to work. The thicker spots gained an advantage because gravity pulled more strongly there. More particles drifted inward. The more that arrived, the stronger the pull became. A feedback loop began as gravity encouraged matter to gather into clumps. Over countless cosmic moments, these clumps grew heavier and tighter until the pressure at their hearts caused hydrogen atoms to fuse. The first stars were born, lighting a universe that had been dark after the early glow faded. The cosmos changed from a uniform fog into a tapestry of stars, each one a brilliant furnace sculpted entirely by gravity's insistence that matter should not remain lonely. The stars themselves gathered into swirling families. Vast spirals, glowing clouds, elliptical cities with trillions of suns. These were galaxies, each one held together by gravity threading through space like a hidden architect. The galaxies formed long filaments across the cosmos, creating something that resembled a web. Gravity does not simply make isolated structures. It arranges relationships. It dictates that a cluster of galaxies will circle one another, rather than drifting endlessly apart. It shapes the lives of stars, decides when they will ignite and how they will die. It pulls dust into planets, planets into orbits around stars, and moons into delicate dances around planets. Without gravity, everything would scatter and dissolve. With it, structure is possible. Our own home lives inside a system designed by gravity. The Earth does not spiral away into the dark because the pull of the sun holds it close. The moon does not abandon the Earth because the Earth's pull is stronger than the tides of space. Even the orbits of planets influence one another through subtle gravitational whispers. There is no solid platform beneath our feet. There is no pillar suspending the worlds in position. Instead, a continuous curvature of space itself guides every path and every step we take. Einstein discovered that gravity is not a traditional force, like magnetism, but rather the bending of the fabric of space and time around mass and energy. A planet like the Earth follows the straightest possible path through this curved geometry, which we perceive as being held in orbit. Gravity therefore acts on two levels. It is a builder of cosmic architecture, forming stars and galaxies from simple particles. And it is a supervisor of motion, ensuring everything dances in orderly orbits and spinning wheels. Without this unseen caretaker, galaxies would rip themselves apart from internal motion and planets would drift into the cold emptiness between stars. Gravity keeps the symphony playing in harmony, yet gravity was supposed to do something else. The early vision of the universe imagined a cosmic tug of war between the outward push of the initial expansion and the inward pull of gravity. Scientists believed that as galaxies spread apart, the attraction between them would gradually slow this expansion. One could imagine throwing a ball upward. It rises but slows under the pull of the Earth. In the same way, the universe should expand vigorously after the Big Bang, then decelerate as gravity tries to reel everything back inward. Perhaps expansion would stop altogether, and the cosmos would collapse once more. Or perhaps the expansion would continue forever yet slow to an almost frozen stillness. Either way, gravity seemed destined to dominate eventually. Every piece of matter exerted this pull. The more matter, the stronger the decelerating effect. Even light contributes energy that gravity responds to. The equations predicting the fate of the cosmos appeared straightforward. Measure how much matter exists. Predict whether the universe will coast to a halt or someday reverse direction. Gravity appeared confident and unquestioned as the steward of the cosmic future. The key expectation was that the expansion should be slowing down. This belief was not an assumption made lightly. It came from mathematics carefully derived and measurements of galaxy motions observed over many decades. The early universe expanded faster because the matter inside it was denser and gravity's pull was correspondingly stronger. Over time, expansion stretched space, diluted matter, and reduced gravity's grip from its youth. But the grip should still be there. It should still be decelerating the expansion right now. To believe anything else felt almost unreasonable. Why would the universe expand faster over time, unless something new or deeply mysterious pushed it? Scientists trusted the laws they knew, and those laws crowned gravity as the ruler over the long-term destiny of everything. The cosmic story seemed set. Gravity had built this grand universe. Gravity would decide how it ends. Except that is not what the universe chose to do. Gravity was supposed to pull harder than the expansion of space. It was supposed to steady the universe like an anchor, always resisting separation. For billions of years, it did exactly that. Galaxies formed in closer proximity long ago because the expansion was slower then. Clusters of galaxies were born from even tighter gatherings. The early cosmos was far more compact, and gravity's authority was unquestioned. Imagine a universe where everything is racing outward from an immense beginning. In those early moments, gravity grabbed the nearest pieces and did not let go easily. That is how stars collected into galaxies and galaxies into clusters. With every passing era, though, expansion kept stretching the fabric of space a little farther. Galaxies drifted apart. Their motions slowed less than expected because gravity's grip was weakening with distance. Still, scientists remained certain that gravity held the long-term advantage. Then something astonishing happened. The universe betrayed those predictions. Instead of slowing, the expansion began to speed up. It was as if some invisible presence had quietly turned a cosmic dial. Suddenly, the push outward became stronger than the pull inward. Gravity, once believed to be the unquestionable master of the universe, seemed unable to keep control over the largest distances. The cosmos had chosen a different fate than the one scientists expected, and that realization shook the foundations of cosmology. To appreciate how shocking this was, think of a giant explosion. Everything flies outward at great speed. Over time, gravity between the fragments slows them, perhaps enough that they eventually fall back toward the center. That is the logic, yet the universe behaves differently. The fragments, which are entire galaxies, are speeding apart faster today than long ago. The normal rules of a simple explosion do not apply. Something entirely new has joined the cosmic story, something not predicted, something powerful and mysterious. This mysterious influence does not act like ordinary matter. It does not clump to form stars or collect into clouds of gas. It does not emit light or absorb light. Its effect is subtle but unstoppable on the larger scales. Galaxies do not accelerate because they are being pushed by wind or particles. The very space separating them is growing more rapidly. Imagine the fabric of the universe expanding like a living thing. Every stretch creates more space. Every new part of that space contributes to the growth itself. The cosmos becomes better at expanding as it expands. Gravity, for all its strength, struggles to fight something that increases its own power as space grows. This change in cosmic behavior did not happen recently in human terms. It began several billion years ago, when the universe had already formed galaxies and clusters. Before that turning point, matter was dense enough to keep expansion decelerating. But as space grew and matter thinned out, something else rose to dominance. Its influence built slowly until the universe crossed a tipping point where gravity could no longer slow the expansion. The acceleration began quietly, without fireworks or sudden calamity, yet it marked the beginning of a new era. a universe ruled more by separation than by union. Even now, gravity still reigns wherever matter is concentrated. Stars hold their planets close. The Milky Way galaxy still wraps its spiral arms securely around hundreds of billions of suns. Clusters of galaxies still orbit their common center, but the spaces between clusters are growing at an ever-increasing rate. There is a horizon beyond which galaxies slip away faster than even light could bridge the gap. Not because they move quickly through space, but because the space between us and them multiplies. There will come a distant time when galaxies beyond our own cluster will fade entirely from view. The cosmos will seem emptier, not because structures vanished, but because expansion carried them forever beyond communication. This leads to a disquieting truth. Gravity built the universe we see. It formed every star and world and atom by pulling things together. But gravity might not be the final authority. The force that is driving expansion faster each day has the power to defeat gravity's influence across the universe. Whether gravity remains queen of local scales or someday loses, even that ground depends on what this mysterious phenomenon truly is. We stand at a moment of cosmic suspense. Gravity is still the architect that shaped everything. But something else is taking the future into its own hands. The acceleration of the universe is not subtle. Over cosmic time, it will only become more dominant. If its strength continues to grow, then gravity's slow, careful work of billions of years could eventually be undone. The universe might not remain a place of structure and harmony. It may become a place where distance and emptiness rule completely. The expansion of space is no longer a background setting. It is the driving force of the entire story. Yet scientists do not fully know what causes it. They have given this unknown source a name that sounds scientific, but hides the ignorance behind it. They call it dark energy, a placeholder term for an invisible power reshaping the fate of everything gravity built. Gravity once seemed unbeatable. It was the quiet but relentless force that organized chaos into beauty. It turned a seething cloud of particles into a universe filled with luminous islands of stars. Every galaxy was a declaration of gravity's triumph. Every cluster of galaxies was a monument to its patience. It sculpted the cosmos from the smallest grains of dust to the largest structures ever imagined. For nearly the entire history of the universe, gravity has been building upward from simplicity into complexity. Yet even as it worked, the seeds of a new power were already present in the fabric of space itself. When Einstein described gravity as the bending of space and time, he found that empty space carries its own kind of energy. That idea sounded harmless at first. Space seemed empty. Why worry about the energy of nothing? But empty space is never truly empty. It has a restless nature. Quantum fields flicker with activity even when there are no particles present. These subtle energies might have seemed too small to matter for the entire cosmos, but on the biggest scales, small effects can accumulate into enormous consequences. Scientists eventually realized that this background energy of space does not dilute with expansion. Matter thins out as space stretches. Light becomes more spread out and loses energy, but the energy of space itself stays constant per unit volume. When the universe was young and tiny, space energy was overwhelmed by dense matter and radiation. Gravity held the upper hand. As the universe aged and expanded, matter thinned. Radiation lost influence. Gravity weakened in comparison. Meanwhile, the energy of space simply waited, patient and unchanged. Eventually, the balance shifted. The universe reached a size where the energy of empty space surpassed the gravity of matter. From that moment on, space energy began driving expansion to accelerate. It was not a sudden overthrow, it was a quiet coup. Gravity lost its cosmic crown without even making a sound. Now space itself is the dominant player in the universe, and gravity has been relegated to local oversight rather than universal command. This teaches a profound lesson. The fate of the universe is not determined only by what we can see. The grand architectures of stars and galaxies are beautiful but temporary creations. The invisible energy woven into the void between them is steering the future. As expansion speeds up, far distant galaxies will one day become unreachable, fading into a silence deeper than any vacuum. The cosmic web that gravity built will unravel strand by strand. Entire clusters will drift apart until each becomes a lonely island surrounded by growing darkness. For now, our cosmic neighborhood remains held together. The Milky Way galaxy and the Andromeda galaxy will still collide and merge in billions of years, because they are close enough that gravity overpowers expansion locally. The galaxies within our own cluster remain bound as well. But beyond that border, the universe stretches like a restless ocean tide. Every moment pulls distant worlds farther beyond reach. We live in a temporary age where we can still observe the wider cosmos. In a far future, even the closest clusters beyond our own will vanish from sight forever. Observers living trillions of years from now may look into the sky and believe they inhabit a lonely universe, unaware of the vastness that once existed beyond their view. Gravity's influence will continue to shrink across the grand expanse. Structures already built will remain protected for a time. But if the force accelerating expansion grows stronger with time, as some theories suggest, then even the most stubborn structures could eventually surrender. There is a fragile boundary between what gravity can hold and what the expansion can break. The question that defines the destiny of everything is simple yet terrifying. Is the current acceleration constant, or will it intensify? If the power of expansion stays constant, then gravity keeps its small dominion. Stars will still form, planets will still circle their suns, clusters will remain intact. The universe will grow emptier, but not destructive. Yet if the energy causing expansion continues to strengthen, then gravity will lose every battle eventually. Galaxies could be pulled apart, solar systems torn into wandering fragments. Finally, even atoms could be stretched beyond endurance. The universe would not simply fade into cold darkness. It would be ripped into pieces by the very space that once sheltered everything. This possibility is known as the Big Rip. It describes a universe where the accelerating expansion becomes a destructive force. Everything gravity ever built could be dismantled. Time itself could lose coherence near the ultimate singularity when space stretches faster than physical law can cope. Though this fate remains uncertain, its mere possibility shows how fragile structure truly is. The cosmos that appeared stable and eternal might only be a temporary arrangement poised between order and dissolution. We stand at the edge of understanding. Gravity gave us stars and worlds. Expansion might take them away. The future depends on the nature of the energy driving the universe apart. Is it steady? Is it growing? Does it change over time? We search the sky for answers, measuring distant supernovas and the quiet glow of ancient radiation left from the beginning. The evidence so far hints at a delicate balance. The universe is accelerating, but only slightly faster than the minimum required for separation. This tiny difference will decide everything. The story of gravity is no longer one of total victory. It is a duel for the future against a silent enemy that only reveals itself through the increasing distances between galaxies. The architect of the cosmos faces a challenger that does not build but unbuilds, and yet the final outcome remains unknown. There are chapters of this cosmic drama still unwritten, and every observation we make brings us closer to understanding which force will decide the end of the universe. The belief that gravity controlled the destiny of the cosmos lasted for most of the 20th century. Astronomers measured the movements of galaxies and watched the universe expand. They assumed that over time gravity would tug harder and slow everything down. The only question seemed to be whether the universe had enough matter for gravity to stop the expansion entirely. If there was just a little too little matter, then the cosmos would continue stretching forever, yet always slowing, like a stone thrown upward that never quite falls back. This was such a reasonable idea that many scientists could not imagine a different outcome. But in the final years of the 20th century, humanity found something that rewrote the future. Distant exploding stars known as Type 1, as supernovas, served as cosmic mile markers. These are special events. They occur when a white dwarf star steals matter from a companion, until its mass reaches a critical threshold. Then it erupts with almost identical brightness each time. Because their true brightness is nearly the same, astronomers can judge their distance by how faint they appear. Compare that distance with how fast the host galaxy seems to be receding, and you get a clear measurement of how the universe has been expanding through time. Teams of researchers in different parts of the world set out to make the most precise measurements ever. They looked deep into space, which means far back in time. Their goal was to see whether the expansion was slowing as everyone expected. They collected data with tremendous patience. They calibrated instruments and checked for any errors that might mislead them. They compared results over and over again. And when the answers finally came back, something was wrong. The galaxies hosting those ancient supernovas were farther away than they should have been if the universe had been slowing down. The only explanation that matched the observations was startling. The expansion of the universe was speeding up. This was not supposed to happen. It completely contradicted the expectation built from decades of theoretical work. If expansion was accelerating, then some unknown influence was acting like a kind of anti-gravity. The researchers who made this discovery approached the data with extreme caution. They asked whether dust could be dimming the supernovas more than expected, making them appear farther. They asked whether the explosions themselves might not be as uniform as believed. They asked whether they had misinterpreted the motions of the galaxies. But every test confirmed the same answer. The universe was accelerating. Gravity was losing the cosmic struggle. When this result became public, it triggered shock and excitement. Many scientists resisted at first. How could the universe behave in a way that seemed to defy the known laws of physics? But gradually the evidence grew too strong to ignore. Other teams repeated the observations. Independent methods confirmed the accelerated expansion. The idea of a decelerating universe faded. A new understanding took its place. The cosmos was not coasting. It was being driven. To explain this invisible driver, scientists introduced a name that sounded like a discovery, but was really an admission of ignorance. They called it dark energy. It did not emit light. It did not clump like matter. It made itself known only through the speeding separation of galaxies. The word dark meant unknown. The word energy meant it affected the dynamics of space. Beyond those simple statements, almost nothing about it was understood. Yet the effect of dark energy was not subtle. It changed the entire future of the universe. If the acceleration continued, then the density of matter would become less significant over time. Gravity would keep losing ground. The cosmic web would stretch thinner. The possibility that everything could be torn apart entered the realm of serious physics. Scientists had uncovered a force that opposed gravity on the largest scales. It was as if the universe had two personalities. One wants to gather, one wants to separate. The discovery brought with it a deep philosophical shift. For most of human history, the cosmos seemed eternal and unchanging. Even once people accepted the Big Bang, they imagined the universe slowly evolving under the steady rule of gravity. Now it seemed the universe was entering a new era, dominated by a force that no one could explain. The future looked unstable and unpredictable. A calm universe coasting gently outward was replaced by one racing ever faster into the unknown. What made the acceleration especially mysterious was the timing. It began when the universe was already several billion years old. Before that, gravity dominated. After that, dark energy took control. Why then? Why not earlier or later? The universe seemed to wait until galaxies and clusters and stars and planets all existed before introducing this dramatic twist. We live close to the moment of transition. That makes our vantage point special in a strange and possibly unsettling way. If dark energy had become dominant when the cosmos was young, there would be no galaxies and no life. If it arrived much later, we might never know it existed. Instead, we appear during the narrow window when the change is visible. Some scientists hesitate to believe such coincidence. They suspect there is a deeper principle we have not yet discovered. Others say coincidence happens. After all, someone has to live at the time of measurement. But the question remains, did the universe save this surprise for the age of galaxies deliberately, or is nature simply stranger than we imagined? The supernova discovery did more than reveal a new cosmic force. It redirected the path of physics research. In the early 2000s, the Nobel Prize in Physics was awarded to the leaders of the teams who discovered the accelerated expansion. Their work opened a door leading into a territory filled with uncertainty and wonder. Cosmologists now had to rethink their fundamental equations. Astronomers expanded their surveys to map the universe with greater precision. Theorists dug into the foundations of space and time, searching for hints of what dark energy could be. As we look deeper into the night sky, the galaxies appear to flee faster the farther away they are. This is not because they are being thrown outward with increasing speed. It is because the fabric of space is stretching more and more rapidly. That stretching changes the way light travels and the way distances grow. It reveals an energy hidden in the vacuum that fights gravity for control over destiny. We find ourselves witnessing a battle we never expected. The universe is not just expanding, it is accelerating, and that changes everything. The idea that space itself could be the source of such power seemed unbelievable at first, but the evidence from those distant, stellar explosions was too clear to deny. When scientists traced the light from ancient supernovas, they were not only measuring brightness, they were reading the history of expansion written in the stretching of wavelengths. Light that began its journey billions of years ago carries within it the memory of how fast space expanded along the way. Those memories told a story no one had expected. The past expansion of the universe was slower than the expansion now. That means something changed. Something began to push harder as the universe aged. To understand how shocking this was, imagine studying a ball thrown upward into the sky. At first it flies quickly, but gravity steadily slows it down. Now, imagine that somewhere halfway through its flight, an invisible force begins to shove the ball faster and faster upward. The motion reverses character entirely. That is what astronomers saw in the cosmos. The universe was expected to behave like that ball. It was supposed to slow. Instead, it accelerated, and the push was not occasional or localized. It acted everywhere in space at the same time. This raised a frightening question. If this unknown force was already winning against gravity and still gaining influence, what would happen in the far future? Would galaxies that are now bound together someday drift apart? Would stars that rotate around the centers of galaxies one day break free and drift into cold darkness? Would planets lose their steady paths around their suns? Might atoms themselves someday be stretched beyond endurance? These ideas seemed like wild speculation at first, but the very fact that cosmic acceleration existed forced scientists to consider all possibilities. A universe that changes course once might change course again. The mysterious nature of this energy made the challenge even greater. Ordinary matter behaves in predictable ways. It responds to gravity by clumping together. It emits or absorbs light. It can be weighed. Dark matter, although invisible, still pulls on other matter through gravity, allowing its presence to be detected. But dark energy did none of these things. It did not gather in lumps. It did not reveal itself in the glow of distant suns. No instrument could collect a sample of it for study in any laboratory. It existed everywhere, yet refused to be seen. To describe dark energy, scientists used an idea called pressure. Not the pressure of air in a tire, but a fundamental property that tells space how to curve. All energy presses on the fabric of space, but dark energy applies a negative pressure. In everyday life, negative pressure might sound like suction. Here it does something much stranger. It causes the geometry of space to curve in a way that makes distant galaxies move apart ever faster. Einstein predicted this kind of effect was possible when he first built his equations of gravity. He even introduced a special term into the mathematics to allow the universe to remain static. Later, he abandoned the idea, calling it a mistake because the universe was discovered to be expanding. Yet decades later, scientists found that something very similar to that abandoned term may be real after all. The thing Einstein once removed had returned under a new name. When the news of the accelerating universe spread through the scientific world, it forced a reckoning. If dark energy existed, then 3/4 of the universe was composed of something entirely unknown. The matter that forms stars and planets and everything we can touch made up only a small minority. The rest was invisible expansion, driving energy, and dark matter holding galaxies together. Reality was more mysterious than anyone had imagined. Every textbook line stating that gravity shapes the universe needed an important correction. Gravity shapes the visible structures. Dark energy shapes the future. This realization carried an emotional weight. Humans had believed that by the end of the 20th century, they had grasped the big picture of the cosmos. They knew how it began and believed they had narrowed down how it might end. Then a single discovery showed that most of the universe's content and one of its most powerful influences was still waiting to be understood. It was as if nature revealed one corner of its grand design, only to hint that behind that curtain lay an even deeper puzzle. The acceleration of the universe also affects the view of the past. Light from very distant galaxies must travel through more and more stretched space, which slows its arrival. The farther we look, the dimmer and redder galaxies appear until they fade completely. The acceleration worsens that effect over time. In a distant future, much of the universe will disappear behind a horizon of expansion. The great structures that gravity built will remain only in memory or ancient records. If intelligent beings evolve trillions of years from now, they might see only one cluster of galaxies and conclude that is all the universe ever contained. This means our era is blessed and cursed. We can still witness the full cosmic landscape, but we know that window is closing. The discovery of cosmic acceleration did not break science. Instead, it broke an assumption. It reminded scientists that discovery often arrives disguised as contradiction. When the universe acts in an unexpected way, that is not a failure of nature. It is an invitation to look deeper. Dark energy remains unnamed in any truer sense. We do not know if it is a property of space itself or something dynamic and changing. We do not know if it is constant or growing stronger every moment. We do not know if it might someday reverse and cause the universe to collapse. We do not know whether it might reach a point where it overpowers even the strongest forces that bind matter together. All we know is that it exists and that its influence is increasing with cosmic time. The discovery that broke the universe is really a discovery that broke our confidence in easy answers. The cosmos is not finished evolving. We are living in a moment when the balance between attraction and expansion is shifting. That uncertainty makes the story more thrilling. The next chapters are being written by space itself as it decides whether to preserve structure or tear everything apart. The acceleration of the universe did more than change the equations of cosmology. It changed what it means to ask about the fate of everything. Before this discovery, scientists imagined only two major endings. One scenario was the Big Crunch, a future in which gravity eventually wins, halting the expansion and drawing all matter back into an enormous collapse. The other scenario was an endless expansion slowing over time, leading to a cold future where stars burn out and galaxies drift in silence but structures remain intact. Both scenarios gave gravity the decisive role. Gravity would either pull everything back or forever struggle yet still preserve the architecture it built. The accelerating universe introduced a new contender. Now expansion itself can overpower gravity. Instead of just drifting farther apart, galaxies might one day fly away from each other faster than any signal can cross the distance. Clusters may unravel into single galaxies. Solar systems may stretch until even planets are no longer held by stars. This is a future where gravity does not merely lose influence, it loses authority. The universe becomes a place ruled by separation. If this acceleration increases without bound, the Big Rip becomes possible. The very things that give the cosmos structure would be erased by the same expansion that once allowed them to exist. Observers on Earth took time to digest the implications. The name dark energy sounded almost like a character in a science fiction story. Yet its presence is supported not only by supernova observations but by the pattern of the cosmic microwave background, the ancient light from the earliest time the universe became transparent. That faint glow carries a map of density ripples imprinted when the universe was young. The size and arrangement of those ripples reveal how space expanded over billions of years. And the answer is consistent with supernovas. The universe accelerated. Dark energy is real. There is no laboratory on Earth where scientists can isolate dark energy and examine it like a substance. It acts everywhere at once, yet is completely invisible. The best they can do is trace its influence through the motions of galaxies and the imprint on the cosmic background. Precision surveys continue around the world and in orbit. Telescopes observe how galaxies cluster on large scales, and how the growth of structure has slowed as dark energy gained strength. Every measurement sharpens the picture, but also deepens the mystery. When the discovery was awarded the Nobel Prize in Physics in the early 2000s, the scientific community celebrated not only the result, but the lesson. The universe still holds secrets large enough to overturn our biggest ideas. Even after centuries of learning how nature works, there are still forces in play that we did not anticipate. Humility is the only reasonable response to a universe that teaches with surprises. Scientists now classify the universe into three main components. A small fraction is ordinary matter, which builds stars and planets and living things. A larger fraction is dark matter, which interacts with gravity but not light, and forms the backbone of galaxies. And the majority is dark energy, which drives the acceleration of space. Everything we see with our eyes and instruments is only the tiniest slice of the true cosmic story. The part that shapes the future most strongly is the part we understand the least. What does it mean to live in such a universe? It means that the expansion of space is not a relic of ancient history, but an active and growing force. It means that the galaxies we observe will not always remain accessible to observation. It means that our place in cosmic time is unique. We are witnesses to a transition, a turning point that divides an era governed by gravity from an era governed by something far stranger. The discovery that broke the universe broke it open. It revealed that the cosmos does not follow a single rule from beginning to end. Forces can change their dominance. Balance can shift. Surprises can emerge that redefine destiny. This understanding also raises a deeper question. What if dark energy itself changes over time? If it grows more powerful, the Big Rip scenario becomes more likely. If it weakens or flips signs someday, gravity could reclaim dominance and pull everything back into a big crunch. If it remains constant, the universe will continue to accelerate, but slowly enough for local structures to survive indefinitely. The truth is hidden in a single number that defines how dark energy behaves. Scientists call it the equation of state parameter. It measures how the pressure of dark energy relates to its density. If that number is exactly -1, then we live in a universe where acceleration will continue steadily. If it is more negative than that, then the acceleration will intensify. If it is less negative, then acceleration could ease. Measurements so far suggest the number is close to -1. But close is not enough. The future of the universe is decided in the decimals. Those decimals could decide whether the cosmos becomes a peaceful ocean of scattered galaxies or a violent storm that tears structure apart. The answer could be written in the data from future observatories that will map the cosmos with breathtaking precision. Perhaps one day we will know the truth. For now, we explore a universe defined more by questions than answers. The discovery that broke the universe did not destroy our understanding. It revealed that understanding was incomplete. It gave scientists a new frontier that stretches across all of space and all of time. We stand on the edge of knowledge, peering into a darkness filled not with emptiness, but with possibility. What force drives the expansion? What does it want? What will it do next? The next chapter begins with the attempt to answer those questions. It begins with the search for the true nature of dark energy. Dark energy rules almost everything, and yet we do not know what it is. More than 2/3 of the entire cosmos is made of this invisible influence that pushes space to expand faster and faster. Ordinary matter, the stuff that forms stars and planets and people, is only a tiny fraction. Even dark matter, which outweighs ordinary matter by a wide margin, bends its knee to the acceleration driven by dark energy. If the universe were a kingdom, then gravity once sat proudly upon the throne as the commander of cosmic evolution. Now a new emperor has taken control, one that cannot be seen, touched, or sampled, one that reveals its authority only by reshaping the universe itself. Scientists give dark energy a simple label, but the simplicity hides a terrifying truth. We know almost nothing about it. It does not collect into galaxies or clouds. It does not shine or absorb light. It does not clump at all. It spreads perfectly smoothly throughout the universe, even as that universe grows. It does not weaken. Space expands, and dark energy expands with it. The more space there is, the more of this strange energy exists. It behaves like an endless well of separation. Its pressure, unlike any known substance, is negative. This negative pressure does not squeeze. Instead, it pulls the geometry of space toward accelerated expansion. The more we look, the more it seems that dark energy is not just part of the universe. It is the dominant force shaping the eras to come. At the core of dark energy lies a number that controls its behavior. Scientists call it the equation of state, but it represents something easier to visualize. It tells us how the pressure and energy of dark energy work together to influence gravity. If that number equals -1, then dark energy is constant in strength. It behaves like the energy of empty space itself. This is called the cosmological constant. It matches Einstein's original mathematical term that he once introduced and later discarded. If this constant picture is correct, the universe will keep accelerating, but it will not tear structures apart. Galaxies inside clusters will remain safe. Solar systems will continue to orbit. The cosmos will grow lonely but orderly. There are other possibilities. If the equation of state is a little less negative than negative, one dark energy could fade slowly over time. In the far distant future, gravity might regain control, and the universe could approach a more peaceful eternity, or even reverse someday. But if the equation of state is more negative than -1, then a much more dramatic outcome becomes possible. In that case, dark energy strengthens as the universe expands. The acceleration increases without bound. Gravity eventually loses every battle from the largest clusters down to the smallest particles. The future becomes a countdown toward destruction. This is the scenario known as phantom energy. Phantom not because it is ghostly though it is, but because it behaves in ways that break our usual rules. Phantom energy grows stronger the more the universe expands. It feeds on the very act of separation. This phantom case might lead to a big rip where every structure is dismantled, galaxies torn apart, stars stripped from their orbits, planets released into chaos, even atoms pulled apart as the expansion of space overwhelms the forces that bind protons and electrons together. It is a future in which the very fabric of spacetime accelerates so violently that nothing can cling to anything else. Time would end at a moment where the expansion becomes infinite in a finite number of years. That idea sounds like the nightmare of a poet, but it is derived directly from the mathematics of general relativity if dark energy intensifies. Of course, no one yet knows whether dark energy is constant dynamic or phantom. We do not even know if it behaves the same everywhere in the universe, or if it might shift character over time. Some researchers imagine dark energy as a kind of rolling field, spreading through space and evolving slowly. They call this idea quintessence. In that picture, dark energy might change its strength as the universe ages. Perhaps we live in a time when it is only beginning to awaken. Perhaps it could weaken again in the future. In that case, the fate of the cosmos might not be predetermined. Quintessence suggests that dark energy is not passive emptiness, but a kind of field similar to the one that filled the early universe during inflation, though much weaker. It might fluctuate. It might interact with other parts of physics in ways we have yet to detect. It might hold the key to understanding why the acceleration began only after galaxies already existed. If quintessence changes slowly, then the transition of power from gravity to dark energy would unfold like a slow eclipse rather than an instant takeover. There is also the possibility that dark energy is tied to something much deeper in the quantum world. Empty space is a storm of virtual particles popping in and out of existence. The energy of those fluctuations is enormous in theory, yet gravity in our universe responds only to a tiny fraction of it. No one knows why the cosmos should have a vacuum energy so small compared with the enormous value predicted by quantum physics. This discrepancy is sometimes called the worst prediction in the history of science. Trying to solve this riddle may be the key to unlocking the true nature of dark energy. Even though we cannot measure dark energy directly, we can map its influence. We look for how it slows the growth of cosmic structures. We watch the way space expands at different times in cosmic history. We measure the subtle distortions of background light that reveal how matter clumps under gravity. All these observations point to the same conclusion. Dark energy is real and it is powerful. If dark energy is the emperor, then matter is its reluctant subject. Stars and galaxies still obey gravity locally, while dark energy commands the larger stage. It is fair to say that dark energy does not destroy what gravity has built, at least not yet. It simply pushes everything apart at a pace that grows faster every moment. It is a ruler that does nothing and everything at the same time. Its power lies not in action, but in the geometry of reality itself. We live in a universe ruled by an invisible monarch. The more we learn about it, the more we realize how little we understand. Dark energy challenges our theories about the nature of time, about the origin of the universe, and about the ultimate future ahead. It forces us to ask whether space has a life of its own. It tempts us to imagine that what we call empty might be the richest substance in existence. And it reminds us that mystery is not a sign of failure. It is the beginning of revelation. Dark energy holds the cosmos in a quiet grip. It does not shout its presence with explosions or with the bright glow of stars being born. Instead, it works in the silence between galaxies. It stretches those distances gently but relentlessly. The farther a galaxy lies from us, the faster it appears to flee, because there is more and more space in between, and that space is expanding. When astronomers measure light from extremely distant galaxies, they find the wavelengths stretched longer and longer into redder colors. This effect, called redshift, is a record of how space has grown over the course of the light's journey. It is the signature of dark energy written into the oldest star fire we can see. The role of dark energy becomes even clearer when we study the largest structures in the universe. Clusters of galaxies linked by grand filaments form a web that spans the cosmos. Gravity works to draw these clusters closer, but dark energy fights back. The growth of structure has slowed over billions of years. The universe continues to expand, but galaxies do not gather into new superstructures as quickly as they once did. Dark energy resists their attempt to come together. It does not destroy clusters that are already gravitationally bound, but it prevents larger ones from forming. Gravity can only build with what it already holds. Dark energy controls everything else. The cosmic microwave background, the faint glow from the first time atoms formed, reveals more clues. That ancient light carries a pattern of peaks and valleys like ripples frozen in time. The scale of those ripples shows us the geometry of the universe itself. When scientists analyze that pattern, they see the unmistakable fingerprint of a universe dominated by dark energy. Only a cosmic acceleration can produce the precise structure observed. It is as if the universe announced its hidden ruler through the slightest possible clues, waiting for humanity to become clever enough to notice. Dark energy rules so completely that it even influences what we can observe. There is a cosmic horizon beyond which galaxies move away faster than light can ever reach us. Not because they are traveling through space so quickly, but because space itself is expanding between us faster than light can cross. That horizon represents a moving boundary between the knowable and the forever unreachable. As acceleration continues, the horizon slowly draws inward, relative to the cosmic landscape. Entire clusters that are visible today will slip beyond that border. Their light will never arrive. They will vanish from the cosmic story as far as future astronomers are concerned. We might ask why dark energy emerged as a dominant force only in the later stages of cosmic evolution. In the first few 100,000 years after the beginning, radiation was in charge. Later, matter held sway as galaxies formed and gravity built the familiar structures we observe. Then, after billions of years, dark energy rose to power. This sequence feels like the changing of eras in a saga with many chapters. First light, then matter, now dark energy. The cosmos did not choose a single ruler for all time. Instead, influence shifted as the universe expanded and matured. The timing of these transitions seems almost too perfect. If dark energy had taken over too early, stars would never have formed. If it waited too long, we would not have the opportunity to detect it. Our existence depends on a delicate balance that scientists are still trying to understand. Some physicists propose that dark energy might be linked to a fundamental field that changes over time. Others suspect that the structure of space-time itself may evolve in ways not yet understood. There are theories about extra dimensions curled into the smallest scales, or about the deep relationship between quantum information and geometry. There are ideas that gravity at the largest distances could behave differently from Einstein's equations. Dark energy stands at the center of all these questions. It might be a static background or a dynamic living phenomenon. The strangest aspect of dark energy is how passive it appears. It does not interact with matter directly. It does not cause atoms to decay. It does not produce detectable particles that we can trap in detectors. And yet, by merely existing, it alters the destiny of the universe. Like a ruler who stays in the palace, but issues commands that reshape entire continents, dark energy governs from a silent throne. It is everywhere at once. It guides the path of every galaxy. It controls the future horizon of what can be known. If we imagine the universe as a grand balance scale, then gravity stands on one side, holding clusters of matter together. Dark energy stands on the other, pushing space to expand more quickly. At first, gravity weighed more. Structures grew, and the cosmos became rich with stars. Now, dark energy is heavier. The expansion adds to its own strength as if it draws power from the increasing emptiness. Over immense periods, its advantage will grow. The cosmic contest is not finished, but its direction seems clear. Separation will continue. Structure will grow more isolated. The universe is heading toward a state where gravity has less and less influence on large scales. Even so, the mysteries continue to deepen. We still do not know whether dark energy is steady or changing. We do not know if its rule will last forever or end suddenly. It could calm in the far future or rage harder until it tears the universe apart. The balance between gravity and dark energy depends on a number that we are still trying to measure with greater and greater precision. The difference between a peaceful future and a catastrophic end might lie in the tiniest shift in that number. Humanity now watches the universe with careful instruments, hoping to catch the faintest sign of what dark energy intends. The unknown emperor has claimed the throne of the cosmos, but its identity is still hidden behind a curtain of unanswered questions. Every observation we make is a small step toward pulling that curtain aside. We seek to discover whether this ruler is benevolent, constant, and stable, or whether its growing strength hints at a darker intention that may someday unbuild everything we know. Dark energy forces us to rethink what it means for something to exist. In a sense, it is the purest example of a presence defined by its influence rather than its form. It does not resemble particles or waves or any of the familiar ingredients of physics. It does not have texture or temperature or weight in the traditional meaning, and yet it carries most of the energy budget of the entire universe. It is as if the orchestra of creation is playing a symphony, and the loudest instrument is invisible to every listener except through the way the music evolves. We hear its power not in a single note, but in the changing tempo of cosmic expansion. Perhaps the most unsettling realization is that dark energy could have been different. If its strength had been even slightly larger in the earliest epochs, then galaxies would never have formed. Matter would have been pushed apart too quickly to gather under gravity. No stars, no planets, no life. Everything we know depends on dark energy being strangely quiet for billions of years before rising to dominance only after structures were already assembled. It waited. Why did it wait? Was it always destined to awaken at this moment in cosmic history, or did something trigger its change in power? The answer remains hidden, and our existence is balanced on that enigma. We often imagine the universe as a place where laws control every outcome. But dark energy teaches that laws can lead to futures that depend on deep subtleties. The difference between a constant slow acceleration and a catastrophic big rip may come down to the faintest shift in the way this energy scales with the expansion of space. The number that defines dark energy's behavior is extremely close to -1. If it is exactly -1, then the cosmos expands forever, yet does not necessarily destroy what gravity has built, if it is even a tiny bit. More negative than destruction awaits in a finite span of time. The ultimate fate of every atom could rest on a decimal place. Scientists construct enormous surveys to narrow those decimals. They send instruments to space to remove the blurring of our atmosphere. They build telescopes on mountaintops to measure the shapes of distant galaxies and the patterns of clustering across unimaginable distances. Each observation adds another stitch in the tapestry of evidence. Slowly the picture sharpens. Slowly the veil over dark energy lifts. But the result is always the same. Dark energy is there. It dominates. It decides. The very existence of this phenomenon suggests our theories are incomplete. Maybe gravity behaves differently on the largest scales than we think. Maybe the geometry of space is not purely defined by Einstein's equations, but by deeper principles involving quantum information. Some researchers explore the idea that space itself emerges from the entanglement of quantum states. If so, then dark energy might reflect the way information arranges itself across the cosmos. Others propose hidden symmetries or hidden fields that operate at indescribably small scales. In each of these visions, dark energy is not a new ingredient added to the universe. It is a clue to the true foundation from which the universe arises. There is even speculation that dark energy could interact with dark matter in ways we barely suspect. Dark matter gathers into halos that form the skeletons of galaxies. If dark energy communicates somehow with those halos, then the growth of galaxies and the push of expansion could be linked in an unexpected feedback. The universe may not separate its mysteries neatly into categories. They may be intertwined in the same deep origin. Dark energy also has consequences for the flow of time. As the universe accelerates faster, the definition of a horizon becomes more important. Beyond a certain distance, events are doomed never to influence us. Their future light can never reach our future location because space expands too quickly in between. That horizon expands outward in an ordinary universe where acceleration is gentle. But in a universe like our own, where acceleration grows, the horizon moves inward relative to distant galaxies. It erases portions of the observable cosmos from any possible contact. Not through destruction, but through isolation so complete it becomes indistinguishable from disappearance. Imagine a far future when countless galaxies once visible have slipped away behind that ever-retreating boundary. The night sky would grow emptier. Historians of the cosmos might look back on our time as a golden age of discovery when humanity could still see the full extent of creation. We are witnesses to an era when the universe is revealing its secrets more freely than it ever will again. That realization carries both weight and wonder. We study dark energy not only to understand the future, but to make sense of the fleeting privilege we have in the present. There is a strange poignancy to the idea that the majority of the universe is made of something that cannot be seen. It challenges our instincts about knowledge. It forces us to accept that the foundation of reality might lie forever beyond the grasp of human senses. Yet curiosity persists. We build machines to extend our sight into the deepest nights. We write equations to express ideas that thoughts alone cannot hold. We search because the universe asks to be understood even when it hides behind silence. Dark energy does not roar like a lion or flash like a supernova. It changes destiny with a whisper, a gentle, continuous push that accumulates into inevitability. It reminds us that power does not always reveal itself through spectacle. Sometimes the most dramatic transformations are those that unfold so slowly that only a mind willing to look across billions of years can notice them. For all its strangeness, dark energy may be telling a story, both beautiful and frightening. The universe is not static. It is not satisfied to stay as it is. It grows. It reaches outward into more space than existed before. It may continue to do so forever, or it may someday turn its expansion into destruction. The Emperor of the cosmos is cloaked in mystery, and that cloak is woven from the future itself. Everything depends on what lies beneath. As long as questions remain unanswered, we continue the investigation. Dark energy is not a puzzle to be feared, but a mystery to be embraced. It invites us to look farther and think deeper than ever before. We live in a universe where the majority of existence is hidden. And yet, through careful observation and daring imagination, we can begin to uncover the truth behind the invisible ruler that commands the stars to drift apart. There is a quiet threshold in the universe that marks the difference between survival and collapse. It is not a wall or a line painted across the stars, but a mathematical boundary that decides whether gravity can keep holding things together. As long as the pull of matter is stronger than the stretch of space, structures remain safe. Galaxies rotate in elegant spirals. Solar systems glide in calm orbits. Atoms contain their particles in tight embrace. But if the expansion grows stronger than any binding force, then the very idea of structure begins to fail. The universe that once built everything through gravity might begin to unbuild everything through expansion. To understand how this happens, imagine a star holding a planet in orbit. Gravity keeps the planet from drifting away, while its motion prevents it from falling straight into the star. Now picture the space between them slowly stretching. At first, the stretch is too small to matter. Gravity easily compensates. But if the stretching continues to accelerate, the orbit becomes unstable. The planet would feel a gentle tug outward from the changing geometry of space. The tightening balance between inward gravity and outward expansion becomes delicate. Eventually, gravity can no longer keep up, and the planet slips free. This same story unfolds on every scale in a future driven by an ever-strengthening expansion. Far from our galaxy, a cluster of galaxies is held together by all of their mutual gravity. But expansion works everywhere. It stretches the distances between galaxies even inside clusters. If the stretch accelerates more quickly with each passing moment, then one day the combined gravity of the cluster will fail. Galaxies will drift apart not because they choose to move, but because the space between them forces the separation. The destruction of structures would not arrive all at once. It would sweep across the cosmos like a slow tide, beginning with the largest objects and ending with the smallest. First, the bonds between galaxy clusters break. Then the individual galaxies lose their unity as stars become too far apart to remain in a shared orbit. Stars that have circled their galactic cores for billions of years would be pulled outward into the growing void. Solar systems would come next. Planets would be released into lonely journeys through darkening space, no longer guided by the warm pull of their suns. The timeline of such a catastrophe depends on how fast dark energy strengthens. If its growth remains gentle, the universe might stretch into emptiness without violence, letting galaxies fade at great distance, but preserving their internal bonds. Yet if dark energy takes on the behavior of phantom energy, then the future becomes a countdown. At first, nothing noticeable changes. The Milky Way remains solid. The Earth continues its yearly path. But the cosmic clock keeps ticking toward a moment when gravity's authority vanishes everywhere. Consider how expansion currently behaves. Each year, space grows a little faster than the year before. That difference is subtle over the short span of human history. Over the lifetime of stars, though, the impact compounds. In a phantom future, the acceleration becomes fierce. The energy of space increases rather than remaining steady. The faster space expands, the more powerful expansion becomes. This loop leads to runaway growth. The cosmos approaches a moment when distances double faster than any force can respond. Even light, the fastest traveler in existence, would not keep up. Astronomers have given this potential final moment a name that is both poetic and chilling. They call it the Big Rip, not a collision, not a decay, a tearing apart. The name describes exactly what occurs if expansion cancels the power of every force that holds matter together. Gravity fails first at cosmic distances. Then it fails within galaxies. Next, it fails within star systems. Eventually, even atoms cannot keep themselves whole. The electron that dances around a proton would be flung away as the space inside the atom expands. What remains after the Big Rip is not fragments or rubble. It is only isolation. Nothing touching anything. No relationships. No orbits. No shapes. No time as we understand it. This idea does not come from imagination alone. It emerges directly from the mathematics of a universe where dark energy grows stronger than gravity, exponentially. The equations show that if the equation of state of dark energy is more negative than -1, the scale of the universe can become infinite in a finite number of years. That phrase almost feels contradictory. Infinite size in finite time. But it means the universe could reach a point where distances blow up instantly relative to the final moments. The last second before the end might stretch into an eternity where everything is ripped apart by pure geometry. To humans living now, such a future is inconceivably distant. If the Big Rip were to occur, it would happen billions, or tens of billions, or hundreds of billions of years from today, depending on the exact strength of dark energy. Our sun would be long gone, our galaxy unrecognizable. Even so, the idea forces us to think about the fragility of everything. We look around and see structure everywhere. Mountains hold their shape. Atoms remain stable. But these are only temporary victories against the restless expansion that dark energy commands. There is something profound in the realization that gravity's creations do not merely fade as stars burn out. They could be dismantled by the universe itself. The cosmos, which gave rise to galaxies and life, might someday erase every trace of them. The arrow of time would not just lead to an ending, but to an unraveling. The same laws that once drew matter together could become the laws that forbid anything from staying connected. Yet we must be careful before committing to such destiny. The Big Rip is a possible future, not a certain one. Observations so far suggest that dark energy might be constant rather than phantom. The difference between peaceful emptiness and destructive emptiness rests on how this unknown energy behaves with time. Our instruments watch the sky, trying to determine whether expansion is merely accelerating or accelerating ever faster. The smallest change in the rate of that acceleration could decide whether the cosmos ends in silence or in violence. We stand at the edge of a question that reaches beyond science and into existential wonder. If everything around us can be unraveled by the expanding geometry of space, what meaning should we find in the structures built by gravity? And if dark energy can tear apart space itself, what does that say about the true nature of the universe? Is creation only the first act in a grand story whose final scene promises dissolution? The answer to these questions lies in the measurements yet to come, in the patterns of distant galaxies, in the faint light from ancient stars, in the decimals of a single cosmic number. Until we know that number with certainty, we cannot know whether destruction waits in the far future, or whether gravity will always protect what it once built. The vision of a universe entering a phase of destruction challenges the very confidence we place in physical laws. We learn in school that forces like gravity and electromagnetism are strong and dependable. Gravity shapes planets and stars. The electromagnetic force binds atoms and brings chemistry to life. Nuclear forces hold together the hearts of atoms in a grip so firm that only the most extreme events, such as the heart of a star, can overcome them. These forces feel eternal, yet a future where expansion becomes unstoppable introduces a shocking possibility. The fabric of space can become more powerful than every known force. Geometry becomes the ultimate engine of change. Stretching becomes stronger than bonding. Existence becomes vulnerable to emptiness itself. To imagine this in practical terms, picture the distance between the Earth and the Sun slowly increasing, because the expansion of space grows stronger near us. At first, the change is incredibly slow. A single year passes, and the orbit is nearly the same. 1,000 years pass, and still the difference would escape all senses. But in a phantom future, as the acceleration compounds, the outward drift accelerates. The balance between the inward pull of gravity and the outward push of expansion becomes unstable. There comes a time when the Sun can no longer hold its planets. They break free and wander alone. A similar fate would reach the stars within a galaxy. The Milky Way has held its stars for billions of years. Stars complete countless orbits around its center, under the influence of dark matter and gravity. But in a runaway future, the Milky Way would lose its ability to keep those stars from slipping away. Each star becomes a lonely traveler in a rapidly growing void. Groups that once formed constellations are scattered like sand in a storm. As expansion continues its assault, the next targets are even more surprising. The force that keeps electrons attached to atomic nuclei is powerful. When lightning flashes, or when a magnet attracts metal, we are witnessing the strength of the electromagnetic force. But even that strength can be surpassed by expansion that grows exponentially. If space inside an atom stretches faster than the electromagnetic attraction can respond, the atom falls apart. Protons and electrons separate and drift into isolation. Matter ceases to exist in any recognizable form. This is not merely destruction of structure, it is the destruction of identity. Everything that gives matter shape and function is defined by relationships. A planet is a planet only because it orbits a star. A molecule is a molecule only because atoms cling to atoms. Even an atom is defined by the bond between particles. The Big Rip threatens the concept of relationship itself. It erases every bond. It redefines every separation as permanent. The most astonishing part of this scenario is that it does not require a new exotic law of nature. It only requires that dark energy behaves just slightly, differently from a simple cosmological constant. If the equation that links its pressure to its energy density dips below a certain boundary, then doom becomes inevitable in the distant ages ahead. The difference between a constant gentle acceleration and a violent ripping apart of everything might be smaller than the difference between a whisper and a sigh. A number with many decimals decides whether galaxies endure or dissolve. The consequences reach further than destruction. They reshape the meaning of time. As the universe accelerates toward the Big Rip, each moment brings a faster pace of change. The horizon that marks what can influence us closes inward more quickly. The interval between cosmic eras shrinks. Stars are torn from galaxies long before planets are torn from stars. Planets are destroyed long before atoms are destroyed. Yet as the final moment approaches, all of these breakdowns begin to compress into a brief, rushing cascade. To an observer near the end, the last few million years, which are impossibly long by human standards, might feel like a blink in cosmic time. The end of everything accelerates along with the expansion that causes it. One could wonder whether life would ever witness such an ending. If conscious beings survive through unimaginable stretches of time and technology, they would feel the universe becoming more and more hostile. Stars drift away until only a solitary sun remains visible in each patch of space. Then that star might escape as well, leaving only darkness. Artificial habitats could preserve warmth and light for a while, but the growth of space does not negotiate with survival. It simply proceeds. Eventually, even the strongest fortress cannot hold matter together. If someone alive in that future tried to measure the expansion, they would see a terrifying pattern. Every pulse of time would reveal a universe growing more violent. The rate of separation would no longer appear smooth. It would race. The sky would not just feel empty. It would feel like a wound widening. There would be no hope of contact with others, no path for travel, no technology capable of resisting the breakdown of nature. The idea that the universe becomes more hostile with age would no longer be poetic. It would be literal. This future is bleak. And yet there is a strange beauty in the scale of the question. It invites us to think not only about the endurance of galaxies, but also about the fate of the laws that govern existence. If dark energy grows forever, does gravity truly disappear? Or does it transform into something else? When atoms are pulled apart, does the concept of matter dissolve into something deeper? Does the Big Rip represent the end of physics or the start of another unknown state? Even more mysterious is the timing. If the Big Rip is real, then there is a fixed countdown. It is not measured by human calendars, but by the accelerating growth of space itself. If dark energy is becoming stronger every moment, then the cosmic clock is speeding up. Time until destruction becomes shorter, not longer for every expansion event. A universe destined for a Big Rip does not fade away in slow, quiet decay. It races toward a finale. Still, we must remain careful thinkers. A possible future is not a promised future. The Big Rip depends entirely on the precise nature of dark energy. Current observations indicate a behavior very close to a constant energy of empty space. That points to a calmer future. But almost every measurement carries uncertainty. And uncertainty leaves a door open to dramatic outcomes. Scientists do not know what dark energy truly is. Without that knowledge, no one can declare the end of the universe with confidence. In the present era, gravity continues to hold our world together. Planets follow their stars. We breathe air held by the pull of our planet. We look at galaxies that remain whole. But dark energy never sleeps. It watches from the edges of the cosmos, increasing its influence one moment at a time. Whether that influence remains peaceful or becomes catastrophic is a question that reaches across billions of years. We stand today in a universe that balances creation and destruction. As long as the decision remains unknown, every star, every planet, every atom stands on the edge of a possibility. The universe either drifts gently into eternity, or it sharpens expansion into a blade. Expansion has always been a fundamental part of the universe. From the earliest moment after the beginning, the cosmos has stretched outward. For billions upon billions of years, this stretching allowed structures to form. As space grew, matter cooled and gravity sculpted galaxies like islands scattered across an expanding ocean. In those eras, expansion was gentle. It made room for stars to shine and for planets to gather dust and form worlds. The balance between gravity and expansion was not perfect, but it was stable enough for complexity to emerge. The idea that the very same expansion could one day become the force that destroys everything feels like a betrayal by the cosmos itself. It is as though the universe, after spending aeons building wonders, suddenly changes its purpose. Instead of being a background upon which the drama of creation unfolds, space becomes the antagonist of its own story. The stage begins pulling apart the actors and the scenery until the play collapses into emptiness. Even today, we can witness hints of this shift. Galaxies farthest from us move away at astonishing speeds, not because they travel through space, but because space expands between us and them. There are galaxies we will never see because their light can no longer outrun the expanding universe. The cosmic horizon marks the limit of influence. On one side are the galaxies we can observe and possibly communicate with. Beyond that horizon lie galaxies forever inaccessible. As acceleration increases, the horizon shrinks relative to the vastness of space. The universe hides more of itself from view. Forgetting becomes a feature of cosmology. In a future ruled entirely by an ever-strengthening expansion, forgetting becomes absolute. Every relationship that defines structure erodes. Clusters no longer gather galaxies. Galaxies no longer gather stars. Stars no longer gather planets. Particles no longer gather into atoms. When expansion reaches inside the smallest spaces, the very definition of matter dissolves. In that moment, all that remains are the simplest ingredients drifting in a space growing so fast that none of them can remain partners even with their closest neighbors. We do not often think of space as capable of violence. We think of collisions and explosions as the dramatic destroyers of structure. A star exploding in a supernova announces its destruction in a blaze of glory. A black hole tears apart a star with catastrophic gravity. Yet these dramatic events affect only small regions. Expansion, on the other hand, is quiet and universal. It does not roar or flash. It does not need heat or fire. It simply changes the rules. And when the rules change enough, everything that once held together must come undone. The most haunting aspect of this scenario is that it would unfold not because of an outside attack, but because the laws of nature themselves evolve with time. The universe would tear itself apart. The same physical equations that once allowed galaxies to form would transform into equations that forbid structure entirely. Physics would not be overthrown by chaos. Physics would declare that permanence is impossible. If such a future awaits, what happens before the final moment? As the Big Rip approaches, the cosmic environment would change in ways we can hardly imagine. Stars would drift into profound solitude long before they are torn from existence. Civilizations, if any remain, would watch their sky empty, decade after decade. Then, year after year. Then, moment after moment. The sense of cosmic community would fade until each surviving island of matter becomes truly alone. Even time itself would gain a cruel sharpness. The acceleration of destruction compresses all meaningful events into the final slivers of existence. Far in the future, a civilization might track the expansion and realize that its era of survival has an expiration date approaching faster than seemed possible. They would know that every technology and every escape plan fails when space itself becomes the destroyer. There would be no refuge, no sanctuary, no new universe to retreat toward. Only an unstoppable acceleration making distance expand faster than thought. And then there is the final question. What exactly is ripped? When we say planets are torn from stars or atoms are ripped apart, we describe the destruction of structure. But what about space itself? If expansion becomes infinite in finite time, does space-time lose meaning? Could the laws governing geometry collapse or change form? The equations that predict this violent growth use the language of general relativity, the theory crafted by Einstein to describe gravity and space-time. Yet near the final moment, the mathematics begins to stretch as wildly as the universe. Our best theories may break before the universe does. Perhaps the end of structure is not the end of existence. Some physicists wonder whether a new phase of reality could emerge on the other side of a big rip. If space-time is part of a deeper information network, then the destruction of classical geometry might represent a transformation, rather than extinction. The universe could be peeling away the familiar to reveal something more fundamental. But this is speculation. No one truly knows. What we do know is that the possibility of such a future depends completely on the nature of dark energy. That nature is still uncertain. The next decades of observations and research will sharpen our understanding of the cosmic acceleration. A tiny change in how dark energy behaves could transform the ultimate fate of everything. If the universe is destined for peaceful expansion, then all structures may survive their own natural lifetimes without interference. If the universe is destined for a big rip, then even those lifetimes become temporary illusions. For now, we continue living in an era where gravity still wins locally. Our solar system remains stable. The Milky Way remains bound. Atoms remain solid. But we do so with the knowledge that the calmness of our world does not guarantee a calm future. The laws of the cosmos are still revealing themselves. Until we know their final form, the future of the universe remains suspended between harmony and destruction. The Big Rip is not inevitable, but its shadow is cast across mathematics and theory, like a warning that the universe is more dynamic and unpredictable than we once believed. The end might not be quiet. The end might not be gentle. If expansion keeps gaining power, the final act will not be a fade to darkness, but a tearing apart of everything that ever existed. The expansion of the universe is not motion in the usual sense. Galaxies are not rushing through emptiness like ships leaving a harbor. Instead, the harbor itself is growing. The space between galaxies stretches, and everything embedded in that space is carried along effortlessly. It is a strange truth that nothing needs to move for distance to increase. When we say the universe expands, we are describing a transformation of space-time itself. The fabric of reality grows. New emptiness appears where there was none before. This is what dark energy commands. In the earliest moments after the beginning of the universe, this expansion was unimaginably rapid. The cosmos ballooned from a size smaller than an atom to astronomical scales in the blink of an eye. That event is called inflation, and it set the initial conditions for everything that followed. Later, expansion slowed and allowed gravity to build galaxies and stars. Only recently in cosmic time has acceleration resumed. Every moment adds more space between the galaxies than the moment before. The acceleration is subtle now, but it is gaining influence. In the far future, the effect becomes impossible to resist. Space-time itself becomes the agent of destruction. To understand how expansion can overpower even local physics, we must picture space-time as something dynamic rather than a static stage. General relativity tells us that matter and energy tell space-time how to curve, and that curvature tells matter how to move. It also tells us that space-time is not rigid. It can bend, it can ripple, it can stretch. When dark energy becomes dominant, it instructs space-time to stretch faster and faster in all directions. The effect is everywhere, even inside galaxies, even between stars, even within atoms. At first, the forces that bind objects remain strong enough to ignore the stretching. But if the acceleration grows without limit, then no bond can resist forever. Imagine a galaxy like the Milky Way. Hundreds of billions of stars orbit a common center. Dark matter provides the gravitational backbone. Even as the universe expands, those stars remain safely bound because the local pull of gravity is far stronger than the gentle stretch of space. But picture a future where acceleration increases drastically. The outward stretch grows faster than gravity can respond. The orbits begin to widen, they lose cohesion. Space-time is not pulling the stars away, as though gripping them with invisible hands. Instead, it is changing the environment in which gravity operates until gravity cannot operate at all. The very equations that once allowed orbits to be stable shift into equations that make orbits impossible. The same principle continues downward through every scale. Solar systems remain intact only as long as space-time expansion remains weak in their neighborhoods. If that weakness disappears, then planets lose their orbits. A world like the Earth would cease to circle the sun and would drift outward into a colder, and colder. Darkness. Seasons would vanish. The sky would no longer show a familiar star. A planet would become a wanderer in a universe that no longer respects the bonds that once gave its path meaning. Even atoms rely on space-time being calm. The electromagnetic force holds electrons to their nuclei, but that stability depends on distances remaining reliable. In a violently accelerating universe, the space inside an atom expands too quickly for the electromagnetic attraction to respond. A proton cannot call back its electron if the space between them grows faster than the force travels. The atom stretches and breaks. Matter as we know it ceases. Space-time does not need to collide or burn or shatter. It simply changes shape and everything inside it falls apart. The most astonishing part of this scenario is that it arises naturally from the mathematics of relativity if dark energy takes the form of phantom energy. When the equation of state drops below -1, the energy of empty space increases as the universe expands. The larger the universe becomes, the stronger dark energy becomes. That creates runaway acceleration. The future becomes a sequence where every moment stretches space-time more fiercely than the moment before. There is a final singular moment when distances expand infinitely, even though only a finite time has passed. This is not poetic exaggeration. It is a prediction of the very same equations that have successfully described gravity for more than 100 years. If such a fate awaits, it will unfold in stages long before the final ripping moment. First, the largest cosmic structures lose their integrity. Galaxy clusters dissolve. Then individual galaxies unravel. Stars drift alone. Later planets become unbound. Eventually, molecules and atoms fall apart. In the last heartbeat of cosmic time, the components of matter themselves lose their coherence. It is a countdown where the scale of destruction shrinks closer and closer to the smallest units of existence. There is something deeply unsettling in this idea. We are accustomed to thinking of physical laws as stable. Gravity does what it has always done. Electromagnetic forces do not weaken with age. Quantum rules remain constant. But a universe ruled by phantom energy would prove that not even the stability of physics is assured. The environment of space-time can change enough to rewrite what is possible. The laws are not wrong. They are simply operating in a reality where their usual strengths cannot overcome the power of accelerated geometry. One of the most compelling reasons cosmologists take this scenario seriously is that the universe has already surprised us once. For most of the 20th century, scientists believed expansion must slow under the pull of gravity. They believed space-time would always resist the urge to tear apart structures. Then supernova measurements revealed that expansion is accelerating instead of slowing. The idea that acceleration might continue to increase is not absurd. It is the logical extension of a universe that refuses to behave in a predictable, linear fashion. But we are far from knowing whether the Big Rip is destiny or only a phantom possibility. Observations so far show that dark energy behaves very close to a constant vacuum energy. The equation of state appears near -1. If that value is exactly -1, then the universe accelerates forever but does not reach a tearing phase. Gravity would still hold galaxies together, even as everything spreads farther apart. Solar systems would survive. Atoms would remain safe. It would still be a lonely future, but a peaceful one. The difference between peaceful eternity and catastrophic destruction lies in the decimal place of one number. That humbling truth defines one of the most important scientific challenges of our time. We measure the expansion of the universe with increasing precision. We map the shapes of galaxies and the behavior of light as it travels across billions of years. Every bit of data helps us refine our understanding of dark energy. Every improvement tightens the uncertainty. One day we may know whether the future ends in a big rip or continues into an endless calm expansion. While this investigation continues, humanity occupies a special moment. Gravity still dominates locally. The world still holds together. We breathe air that clings to Earth. We orbit a sun that remains steady in the sky. But the cosmic balance has shifted. Dark energy is already the emperor of the large-scale universe. It controls the growth of space-time. It shapes the cosmic destiny. We live in a brief age when both creativity and destruction are possible. Galaxies still shine, stars still form. Yet the seeds of eventual dissolution might already be sown in the silent expansion all around us. Space-time is the most fundamental structure. Everything else is built upon it. If the foundation itself becomes unstable, nothing above it can remain whole. A future where space-time accelerates into chaos is a future where nothing can resist the pull of separation. What begins as gentle expansion could evolve into a force that forbids connection of any kind. The question facing cosmology is whether the universe has already chosen that path. For now, the observable universe remains a place where binding forces win against the stretching of space in our neighborhood. But we must not assume permanence. The laws that govern space-time may still be keeping secrets. Dark energy is not fully known. The future is not set. We look into the deep night not only to witness the cosmos as it is today, but to find clues about the shape of tomorrow. The battle between attraction and expansion continues. One day, that battle might be decided not by the collapse of matter into dense clusters, but by the victory of emptiness itself. We now live in an age when the universe itself has become a laboratory. Each photon that arrives from a distant galaxy brings information about how space has stretched along its journey. Each cluster of galaxies tells a story about how structures form under the growing influence of dark energy. Instead of speculating blindly, we can test the future written in starlight. Observations have become our compass in a cosmos that no longer behaves as expected. And slowly, a pattern emerges. It tells us that dark energy is real and powerful, but it also whispers that perhaps the universe will not end in a violent tearing apart. Perhaps the future might remain calm even as the galaxies drift farther and farther away. The European Space Observatory, known as Planck, mapped the oldest light in the universe with extraordinary precision. That light, known as the cosmic microwave background, is the echo of a time when the cosmos was only a few 100,000 years old. It is like a photograph from the beginning. Frozen into that photograph are tiny temperature differences that reveal how the universe expanded during that ancient era. Those ripples show that dark energy had not yet taken control. In those early times, gravity was the master. Matter gathered into clumps. Structure grew. The universe had a clear direction. But as billions of years passed, something changed. Supernovas became our most direct evidence. Their brightness and redshift reveal that the expansion has been accelerating for the last few billion years. Gravity has been losing ground. The speed at which galaxies separate from each other is no longer slowing, it is picking up. Yet even with that acceleration, galaxies remain stable, clusters remain bound. This tells us something important. Whatever dark energy is doing, it has not yet begun to threaten the structures gravity built. To quantify what the observations mean, we use a single number to describe dark energy's pressure relative to its energy content. That number is extremely close to -1. If it were slightly less negative, expansion would still accelerate, but the future would be gentle. If it were more negative, the universe would be steering toward destruction. The measurements so far allow only a small range of possibility. Dark energy seems to behave almost exactly like a cosmological constant. It does not appear to be growing stronger over time. If those indications continue, then the Big Rip becomes unlikely. Structures will survive. Galaxies will endure for trillions of years, even as the universe continues to expand. There are other lines of evidence that point in the same direction. The distribution of galaxies across colossal distances reveals a pattern called baryon acoustic oscillations. These patterns measure the scale at which galaxies cluster together. They give us another ruler to measure the expansion history. When astronomers compare this ruler across time, the result confirms that acceleration is real and that dark energy seems steady rather than increasing violently. Gravitational lensing. The bending of light by massive structures also helps reveal the influence of dark energy. When we study how clusters of galaxies warp the images behind them, we learn how matter clumps over time. Dark energy suppresses the growth of clumps by stretching the universe faster. The more precisely we measure that suppression, the better we understand the nature of the acceleration. And once again, the evidence points toward a stable dark energy that does not grow out of control. Even though the signs discourage the most catastrophic future, they do not rule it out entirely. There remains room for surprise. Small deviations from a perfect cosmological constant are difficult to detect. It could be that dark energy changes slowly, in a way that only becomes obvious over trillions of years. Or perhaps it has cycles we have not yet witnessed. The universe is vast and patient. Sometimes it changes in ways that require ages to reveal. There are also deep theoretical puzzles that keep scientists from feeling satisfied. Quantum physics predicts that empty space should have far more energy than we observe. If we added up every allowed quantum fluctuation, the density of dark energy would be higher by an astounding degree. Yet the universe seems almost finely tuned to have a tiny amount of acceleration. It is almost as if something cancels most of the vacuum energy, leaving behind only the faint remainder we call dark energy. The origin of this balance remains one of the greatest mysteries in all of science. Because of uncertainties like these, researchers do not allow themselves to assume the universe will remain peaceful forever. There may be hidden dynamics that we have not measured yet. There may be evolutions in space-time that have not begun. The equation of state could change from slightly benign to dramatically dangerous. The future might hold more than one cosmic phase. The universe has already changed its behavior once when acceleration began. Change can happen again. Even if dark energy remains constant, the cosmological future is still unlike anything that came before. Gravity will eventually exhaust its ability to form new stars. The existing stars will burn out, leaving only cold remnants. Galaxies become lonely islands adrift in a sea that expands too rapidly for them to see or hear any others. It is not destruction, but it is abandonment. The universe becomes a place of isolation and silence where only the nearest matter remains visible. Still, this outcome feels almost merciful compared to a big rip. In a constant dark energy future, galaxies remain whole, planets continue to orbit, atoms remain stable. Life, if it can adapt to cold and darkness, might endure deep into the coming eras. Civilization might find ways to gather energy from black holes or from proton decay if such decay exists. The cosmos could remain habitable in pockets for inconceivably long spans of time. So what do the observations say clearly? They say that the universe is accelerating. They say that dark energy dominates cosmic evolution. They say that gravity will never again shape the large-scale future. But they also say that expansion is currently calm enough for structures to remain protected. They tell us that the nightmare scenario of universal destruction is not favored by the evidence we have today, and yet mystery remains. We do not know what dark energy is. We do not know why it has the value it does. We do not know whether its rule is temporary or permanent. We do not know whether the quiet expansion we observe is a pause before a new and more dramatic shift. We continue to gather data because the story is still unfolding. New instruments will measure the universe with unmatched precision. Each new observation may narrow the possibilities. Each new result may reveal a hint of the future we cannot yet see. For now, the most responsible conclusion is a humble one. The universe is accelerating. The acceleration seems steady. But the truth about dark energy lies deeper than we can currently reach. The fate of all structure hangs on that truth. Until we find it, the future remains unwritten. Gravity has shaped the universe from the first moment matter cooled enough to clump. It turned scattered particles into giant clouds. Those clouds collapsed into stars. Stars gathered into galaxies. Galaxies grouped into clusters, forming a cosmic web that stretches across the visible universe. Every mountain and moon and molecule owes its existence to the gentle but persistent pull of gravity. It is the architect of structure and the maker of order. But gravity does not rule forever. The expansion driven by dark energy grows stronger with time. Gravity grows weaker as matter spreads farther apart. The future of everything depends on which of these forces changes more quickly. There are several possible fates for the cosmos. Each one depends on the amount of matter in the universe and on the way dark energy behaves. These futures are not myths or metaphors. They emerge directly from the laws of physics. They are possibilities written into the universe, like different endings in a story whose final pages have not been chosen. The first possible ending is called heat death. In this scenario, dark energy remains constant and continues accelerating the expansion gently. Galaxies drift apart until each one exists in its own island of space, cut off from all others. Stars burn their fuel slowly. Over unimaginable spans of time, they die and leave white dwarfs, neutron stars, and black holes. Even those remnants slowly fade. Black holes evaporate through a slow leak of energy, known as Hawking radiation. After a time so vast it may as well be eternity, the universe becomes cold and dark and empty. No new stars form, no new structures arise. Everything becomes thinly spread, isolated and still. Gravity does not lose by catastrophe. It loses by exhaustion. It simply runs out of chances to build. A second possibility is a return to the dominance of gravity. If dark energy weakens over time or even reverses, then expansion could stop. The universe would reach a maximum size, then begin to shrink. Gravity would gather galaxies closer and closer. Clusters would collide. Stars would fall toward each other. Temperatures would rise. Eventually, everything would collapse into a final singular state. This fate is called the Big Crunch. It is like rewinding the beginning of the universe, but in reverse. If the universe is closed and heavy with matter, gravity wins the long war and pulls all creation back into the furnace that birthed it. Some scientists think the Big Crunch might not be a true end. If the collapse triggers a rebound, a new expansion could begin and create a new universe. This idea leads to cyclic cosmologies. Repeated cycles of expansion and collapse may stretch backward and forward through time far beyond the memory of any single epoch. Each cycle might create new physical conditions, new stars, new galaxies, and perhaps new forms of life. In such a cosmos, death is only the end of a chapter, not the end of the story. Gravity would still fail temporarily, but it would rise again each time the universe begins anew. There is yet another possibility. The universe might approach a state where dark energy changes character. Instead of staying constant, it might evolve like a field that slowly rolls toward a new equilibrium. In this future, the acceleration might weaken, the universe might coast, or the geometry of space might change in ways we cannot yet predict. There could be transitions more dramatic than any we have seen so far. The cosmos could enter a phase governed by rules not yet discovered. In that case, gravity might not be defeated or victorious. It might be transformed. All these possibilities hinge on the same unknown truth. What is dark energy, and how does it evolve with time? If its equation of state remains exactly negative, one expansion continues forever but does not grow violent. If that number is less negative than -1, then acceleration weakens eventually. If the number is more negative than -1, then we enter the path that leads to the Big Rip. The entire universe is balanced on a single line in the sand drawn by mathematics. We do not yet know which side we stand on. The evolution of gravity adds another layer to this puzzle. Gravity is not simply a pull between objects. It is a manifestation of space-time geometry. When matter spreads thinly, gravity becomes weaker. When space stretches faster, matter becomes even more spread out. When matter becomes diluted, structure stops forming. The future becomes a place where galaxies no longer collide to ignite new bursts of star formation. Gravity cannot build what no longer exists close enough to gather. Even if gravity never fully loses power, its opportunity fades. There are also theories that suggest gravity is not fundamental. Some researchers propose that gravity emerges from something deeper, like the thermodynamic behavior of quantum information. In those models, space-time geometry is not a background, but a result of countless hidden degrees of freedom interacting. If gravity is emergent, then its failure at large scales might not mean destruction. It might signal a change in the underlying rules of the universe, a shift in the informational structure that gives rise to space-time. If that is true, then the end of gravity as we know it might not be a catastrophe, but a phased transition in the universe's architecture. We consider these futures not because we are obsessed with endings, but because understanding the ending reveals the meaning of everything that comes before. If the universe fades into cold silence, then the struggle of matter to form structure is a temporary miracle against an inevitable background of emptiness. If the universe collapses and begins again, then the cycle of creation is eternal, and every galaxy, every star, every life becomes part of a grand rhythm. If the universe tears itself apart, then existence is fragile, and the structures we see today are only fleeting configurations of a restless space-time. Right now, our moment is defined by balance. Gravity still holds planets around stars. Stars still shine within galaxies. Galaxies still dance in clusters. But dark energy has already claimed the wide spaces between those clusters. The future is being written in the rate at which distant galaxies accelerate away from us. Scientists build telescopes not only to explore the past, but also to glimpse the future. They examine the oldest light and the most distant galaxies to learn how expansion has changed through time. They search for hints that dark energy might be evolving. They refine their measurements of the cosmic equation of state one more decimal place at a time. Every improvement in precision cuts away possibilities. Every measurement narrows the futures still allowed by the data. The fate of gravity will not be decided by hope or fear or imagination. It will be decided by nature, and nature is still revealing her intentions slowly, photon by photon. Perhaps gravity will hold on to its influence forever in small sanctuaries where matter remains bound. Perhaps gravity will return triumphant after dark energy fades. Perhaps gravity will lose completely and watch the structures it built dissolve into the accelerating void. Each scenario is consistent with the laws we know. Each one awaits confirmation from the universe itself. We do not yet know whether gravity's story ends in quiet solitude or fiery collapse or unstoppable destruction. We only know that the answer is encoded in the cosmos. And as long as stars shine and telescopes watch the sky, we will continue following the trail of clues left in the deep darkness between galaxies. Deep inside the mathematics of space-time, a quiet revolution has begun. Some physicists suspect that gravity is not a fundamental force like electromagnetism or nuclear interactions. Instead, they imagine that gravity might arise from something deeper and more mysterious. It may be a side effect of information. It may be the way the universe organizes the countless invisible bits that encode reality. In this perspective, space-time itself is not the smooth fabric we imagine. It is woven from quantum threads of information. When those threads rearrange, gravity changes, structure forms, worlds appear, the cosmos becomes knowable. But if gravity can emerge, then gravity can disappear. And that possibility could reshape how we think about the end of everything. The idea that space and gravity come from quantum information has roots in the study of black holes. Black holes are objects so dense that nothing escapes their gravity, not even light. Yet they obey laws that closely resemble thermodynamics, the science of heat and entropy. Entropy measures the number of hidden microscopic configurations that make up a system. A cup of water has enormous entropy because its molecules can arrange themselves in many different ways. A perfectly rigid crystal has lower entropy because its atoms have fewer ways to move. Black holes strangely behave like objects with entropy. They have temperature. They emit faint radiation. These facts puzzled scientists until they considered a daring possibility. Perhaps black holes are not simple objects, but vast storages of information. This speculation led to the holographic principle. It states that the information needed to describe a three-dimensional region of space may actually be encoded on its two-dimensional boundary. Just as a hologram stores a full image on a thin surface, the universe might store its deepest information along surfaces rather than volumes. If this is true, then gravity might be the way those information bits arrange themselves to create what we perceive as matter and space. One researcher named Eric Verlinde proposed that gravity arises from entropy. In his view, objects move toward each other because doing so increases the number of ways the underlying information can be arranged. In other words, gravity could be like a tendency for the universe to increase its entropy, not by creating chaos, but by forming structures that maximize informational possibilities. This is a striking reversal of traditional thinking. Gravity looks like a force that builds order. It forms stars and planets. But at a deeper level, that order might actually allow more complexity, which means more entropy. Another path to emergent gravity comes from ideas about quantum entanglement. Entanglement links particles across distance, making their states dependent no matter how far apart they travel. Some physicists suggest that space-time geometry itself arises from patterns of entanglement. If you change those patterns, you change the shape of space. In this picture, gravity is the result of entanglement, trying to maintain coherent geometry. Space and gravity are made not of matter, but of relationships. These ideas remain unproven. They are bold and complex, but they offer a new way to think about the great cosmic struggle between gravity and expansion. If gravity is not a fundamental law, then what happens when the universe reaches a point where this emergent process can no longer sustain structure? Perhaps dark energy increases the entropy of empty space faster than entanglement can build geometries. Perhaps the information network that creates space-time begins to unravel. In that scenario, the failure of gravity during a big rip would not be a breakdown in physics, but a change of phase. The universe would enter a state where space-time no longer behaves like a smooth structure. Locality would dissolve. Distances would lose meaning. Information itself might disperse. Consider what this means for the future. Imagine a world where expansion has accelerated so violently that even atoms cannot remain bound. At that moment, gravity has already lost its power. But the process might not stop there. If space-time emerges from entanglement and entropy, then expansion might tear those entanglement links apart. When all entanglement ends, geometry collapses. There is no space left to stretch. There is no time left to flow. The universe becomes a sea of disconnected quantum fragments with no concept of near or far. This would be the death of space-time. Not destruction by explosion or collapse, but a quiet unraveling of the rules that define existence. Or perhaps the unraveling marks the birth of something new. If the physics that created our universe from pure information can transform that information again, then the Big Rip could be an act of creation. The transition might produce a new reality with new rules and a new form of order. The universe may not fear endings because every ending could be the beginning of a deeper layer. This does not remove the tragedy embedded in loss. Everything familiar, including the bonds that create matter, would vanish. But in emergent gravity, theory existence does not rely on atoms or stars. It relies on information. And information does not simply disappear. It reorganizes. If that is true, then the end of gravity is not the end of reality. It is the restructuring of reality from the ground up. Even the current balance between gravity and expansion may reflect an equilibrium in the information structure. The rise of dark energy could signal a shift towards states that favor more entropy. Gravity fought a long war constructing galaxies and stars. That construction created order at large scales, but increased entropy overall by enabling complexity. Now perhaps the universe seeks to enlarge its entropy even further by dissolving structure. Expansion opens more possibilities for the information hidden within empty space. The battle we observe could be the natural evolution of a universe driven not by purpose, but by statistics. These ideas remain on the boundary between theory and imagination. We cannot test them directly yet. We do not know whether gravity truly emerges or whether space-time is truly holographic, but the hints grow stronger. Black hole physics continues to connect geometry with information. Quantum theory continues to reveal that entanglement is far more important than previously believed. The universe keeps reminding us that the world beneath our perceptions operates by laws stranger than any dreamed by early cosmology. If gravity is emergent, then our perspective on fate must also emerge into something new. The collapse of structure may not be doom. It may be transition. The big rip, if it occurs, might be the moment when the visible universe sheds its familiar form to reveal the informational architecture beneath. A transformation so profound that all earlier phases become like childhood memories of reality. A universe shed of its geometry could prepare to rebuild itself in a new and unimaginable way. We study these possibilities because knowledge allows us to replace fear with curiosity. The universe does not owe us comfort. It does not promise eternal stability, but it does offer mystery, and mysteries are invitations to explore. The more we learn, the more we realize how much remains hidden. The future of gravity may involve collapse or silence or transformation beyond comprehension. Whatever the answer, it is already written in the quantum information that shapes the cosmos at every moment. From the moment the universe began, it has been engaged in a quiet struggle between structure and chaos. When everything was young and blazing hot matter existed as a near-perfect uniform fog of particles. There were no stars or planets or galaxies. Nothing had yet taken shape. That early state possessed an enormous amount of energy, but very little structure. Gravity introduced a new possibility. It allowed small regions to become slightly denser than their surroundings. Those denser regions pulled in more matter, which increased their pull. The first clumps formed. Then the first stars ignited like sparks in the darkness. Creation had begun. In a sense, the universe was choosing order over disorder. Gravity was helping matter organize itself into something intricate. But that choice appears to violate a fundamental rule called the second law of thermodynamics. That law says entropy always increases. Entropy is often described as disorder, but it is more than messiness. It is the measure of how many possible microscopic configurations exist. A broken vase has higher entropy because there are many ways the pieces could scatter. A perfectly sculpted statue has lower entropy because only specific arrangements form its shape. If entropy must always rise, how can gravity create order? The answer is that gravity creates order in one place only by increasing overall entropy even more in another. When a cloud of gas collapses into a star, it heats up and radiates energy into space. That radiation spreads out and increases entropy. The loss of complexity in the star-forming region is more than compensated by the gain in the surrounding universe. Order and chaos are not opposites in conflict. They are partners shaping the flow of cosmic time. Structure may be the visible product, but entropy is always the accountant that keeps the books balanced. Dark energy adds a new twist to this balance. Its influence makes space expand faster. As space expands, matter spreads thinner. Stars form less frequently. Structure becomes harder to build. The future begins to favor simplicity again. Entropy still grows because more and more of the universe becomes cold and empty. The battle between structure and disorder shifts toward emptiness as the dominant state. Gravity still forms islands of matter where conditions allow, but dark energy is draining the oceans around those islands, making them more isolated with each passing era. If the universe continues along this path, it becomes a place where entropy reaches a maximum. That state is called thermodynamic equilibrium. It is a condition where nothing interesting happens because all possibilities have already been exhausted. No temperature differences remain to drive motion. No chemical potentials remain to drive reactions. No gravitational collapse remains to build new structures. In such a world, entropy has won entirely. the cosmos relaxes into a state of endless stillness. But for now, the universe is not still at all. It is a boiling interplay of forces competing to shape existence. Gravity is still pulling matter into galaxies. Nuclear furnaces inside stars are still turning hydrogen into heavier elements and releasing energy into the void. Black holes are still feeding on matter and warping space-time. Entropy increases at every step of this activity. Complexity continues to blossom like a brief flare of creativity in a universe that otherwise prefers calm. From the perspective of modern cosmology, the universe does not fight against disorder. The universe uses order as a tool to increase entropy. Galaxies and planets and life are part of that process. We are the observers because gravity created structures stable enough to develop consciousness. Yet our existence adds to the cosmic entropy budget too. Life uses energy gradients. Civilization consumes fuel and produces heat. The rise of complexity accelerates entropy growth. Existence itself cooperates with the arrow of time. This is why dark energy may eventually dominate completely. After enough structure forms, the most efficient way to increase entropy further is to let structure fade away. Expansion dilutes matter and spreads energy thinly across a growing volume. It is as if the universe knows that emptiness is the ultimate state of maximal entropy. Gravity is allowed a period of creation because that process drives entropy upward rapidly. But once the universe becomes mature and structure reaches its peak, there is little left for gravity to accomplish. Dark energy then becomes the main hand guiding the future. It ensures accelerated expansion. It ensures isolation of structures from one another. It ensures that the universe moves toward a future where entropy dominates every corner of creation. In this view, the universe is not being destroyed. It is completing its mission. There is something astonishing in this realization. We often imagine existence as a battle between life and decay, between galaxies and emptiness, between gravity building and dark energy tearing apart. Yet the deeper truth might be that both sides are working toward the same ultimate goal. Entropy must rise. That is the law. Gravity raises entropy through the creative destruction of star formation. Dark energy raises entropy by stretching space until structure loses meaning. The universe does not fight against disorder. It embraces disorder as the guiding principle of time. Still, we cannot help but feel a sense of melancholy when imagining the far future. The stars that now shine across billions of light years will vanish behind cosmic horizons. Their light will never reach new eyes. Civilizations, even if they endure for ages, will eventually face the shrinking sky. Every beacon of creation will be swallowed by the vastness of accelerating expansion. The universe will have chosen silence over song. Yet there exists a bright perspective as well. The fact that we live during the era of stars is extraordinary. We are here at the crest of cosmic complexity. The universe has built a stage where life can contemplate its own origins. That may be the rarest moment in all of existence. Far in the future, when entropy rules completely, there may be no observers left to marvel at the cosmos. Consciousness is a product of the temporary alliance between gravity and energy. We are witnesses to the universe's most creative age. This understanding does not make the future less mysterious. Dark energy still could change. The universe may not settle into quiet emptiness. It may transform again. The structures of information that generate space-time may rearrange. The battle between creation and decay could shift into a new domain we cannot yet imagine. Entropy may continue rising, but the path it chooses might surprise us. For now, we watch, we think, we measure. We exist at the intersection between order and chaos. We are the brief flicker of meaning in a universe driven toward simplicity. And that fleeting nature only makes our moment more precious. We live in a universe suspended between two destinies. Gravity still holds our world safely in orbit. Stars still shine across the darkness. Galaxies still swirl in grand formations shaped by ancient forces. Yet dark energy has already claimed the deep expanses between those galaxies. The fate of everything depends on which of these forces changes first. A single number hidden in the physics of the cosmos waits to determine whether the universe will fade peacefully or tear itself apart. That number is the dark energy equation of state. It measures how dark energy pushes against the fabric of space-time. It is astonishing that the destiny of all matter, from giant clusters of galaxies to the atoms in your body, may hinge on whether that number remains equal to -1 or drifts above or below it over unimaginable stretches of time. If dark energy remains constant, gravity will lose its influence slowly. The stars will burn through their fuel. Black holes will consume what they can and later evaporate. After ages beyond comprehension, the universe will slip into cold stillness. It is a peaceful eternity. No violence awaits, only silence. But if dark energy grows stronger over time, then expansion will accelerate faster and faster. One day galaxies will unravel. Later planets will lose their grip on their suns. Eventually atoms will be unable to resist the expansion of space inside them. The universe will end in sudden and absolute disassembly. This future is called the Big Rip. It is the most catastrophic end we can imagine, not because it burns or crushes, but because it removes the very conditions that allow space to hold matter together. There are other possibilities too. Dark energy may weaken, expansion may slow, gravity may return as the master of creation. The universe could collapse into a dense final state and perhaps rebound into a new beginning. A cycle of cosmic births and cosmic endings could repeat without limit. In that scenario, the end of one universe becomes the seed of another. Existence would be eternal, and each version of the cosmos would be a single beat in a never-ending rhythm. There is no certainty. All these futures remain possible because dark energy remains mysterious. This uncertainty is not a sign of ignorance, but a sign of the curiosity driving science forward. We are not content to watch the sky. We measure its motion carefully. We track distant galaxies. We read the ancient light from the earliest moments. We refine our understanding continually. Each new telescope, each new instrument brings us one step closer to the truth. The future of the universe is not guesswork. It is a puzzle with pieces scattered across billions of light years. Humans are gathering those pieces, one observation at a time. Think about the remarkable position we occupy in cosmic history. For most of time, the universe was too chaotic or too slow to form observers who could question its nature. In the distant future, the universe may grow too empty and cold for anyone to ask why stars once shone. But now, in this brief age, there are galaxies full of light and planets warm enough for life. Consciousness appears just as the universe reveals its secrets. We are here at the intersection between a creative past and an uncertain future. This moment may be the only time when a species can both exist and understand the cosmos around it. Our very ability to contemplate the future gives significance to the present. The universe has spent nearly 14 billion years arranging matter into the complicated forms needed for awareness. It shaped stars that forged elements. It built worlds where chemistry could explore possibilities. Eventually, it created living systems that learned to think, and those systems developed curiosity and reason. Through that curiosity, we have become witnesses to the grandest story ever told. A story about the birth, growth, and possible demise of everything. Knowledge does not erase the emotional weight of cosmic endings. It is natural to feel awe or fear when imagining the disappearance of all structure. But the universe has never promised permanence. Stars live and die. Civilizations rise and fall. Even galaxies change over time. What matters is that we use our moment while we have it. Understanding the universe honors the fragile chance we have been granted. To know something about existence is to participate in existence more fully. there is another perspective that offers comfort. Even if structure fades, the information that shapes the universe may not vanish. Physics suggests that information cannot be destroyed. It can change form, it can move to new states, it can hide, but it still exists. If the Big Rip happens, then the geometry of spacetime may fall apart, yet the deeper informational essence could survive in new configurations. The universe may not end, it may transform. What looks like destruction in familiar terms may be birth in unfamiliar ones. We cannot say for sure. And that uncertainty is powerful. It means the cosmos is not a closed book. It means discovery is always possible. Each answer creates new questions. Every new mystery invites us to keep exploring. The sky above us is not only a reminder of the past, but also a promise about the future. As long as stars shine, we will search their light for clues. As long as time flows, we will wonder where it leads. Perhaps one day, far from now, a distant civilization will look back across cosmic time and marvel that we once lived in the era when the fate of the universe was still unknown. They might envy us for our sense of possibility. They might admire that we dared to ask questions bigger than ourselves. They might be grateful that we paved a path of knowledge that allowed them to understand their place in the cosmic story. Gravity built the universe. Dark energy may unbuild it. The future will reveal which force has the final word. But even if the universe heads towards silence or collapse or transformation, we are part of its journey. We are the rare observers who glimpse both the brilliance of creation and the mystery of destiny. The universe gave us eyes to see and minds to ask. It trusted us with questions that stretch the limits of imagination. Our fate rests on a single number, a whisper in the mathematics that governs existence. The story is not finished. Reality is still choosing its ending, and while it chooses, we are here watching, thinking, and trying to understand. That alone makes this era extraordinary. The end is not written yet.